In this video, we're going to look at splitting, which is a feature of proton NMR. In proton NMR or hydrogen NMR, peaks can split due to the magnetic field of the hydrogen atoms responsible for the peak being affected by the hydrogens on neighbouring or adjacent carbon atoms. The splitting pattern can give us information about the number of adjacent or neighbouring hydrogen atoms, which can be used to work out the structure of a compound, which is what we're going to look at here. Lastly, there's something called the N+1 rule, which will help us understand what's going on when we interpret this proton NMR spectrum. Now, since this video is about proton NMR and splitting, I'm going to quickly go through these other analytical techniques. So this is a combined analysis problem where we've got an unknown compound that consists of carbon, hydrogen and oxygen. The first thing we do with something like this is treat the percentages like masses and work out the empirical formula. And to do that, we do the percentage mass over the mass from the periodic table to calculate moles. Then in the next step, we divide by the smallest. And we end up with a ratio 2 to 4 to 1. After we've got that empirical formula, the simplest whole number ratio, we work out the molar mass of this and compare it to the molar mass from the M plus peak, so the peak furthest to the right on the mass spectrum. This gives us the molar mass of the actual formula. So we've worked out the molar mass of the empirical formula to be 44, while the molar mass of the actual formula is 88, which is twice that. That means the molecular formula must be 2 times the empirical formula. So it must be C4H8O2. We can see we have 2 oxygens in this unknown compound, and we can start thinking about functional groups that it could possibly be. One of these could be a carboxylic acid. It could also be an ester. Maybe it has an alcohol group and something else. So to confirm this, which functional groups are present, we can look at the infrared. Now for this you'd need a data sheet, and I cover infrared in another video, but this sharp peak around 3000 is due to CH. The sharp peak around 1750 is a carbonyl, and there's also a carbon single bonded to an oxygen absorption here, just within the fingerprint region. And this suggests we have an ester functional group. So in these types of questions, we have to piece together all this kind of information like a puzzle. Next, we'll look at the carbon NMR spectrum, and with the use of a data sheet, we can identify the types of carbon from the chemical shift values. I've got a data sheet here, so this one has the values, the chemical shifts for the carbon NMR, and this one has the chemical shifts for the proton NMR, and this is what I'm using. So I'm looking at the values on this x-axis and comparing them to those on here to identify the type of carbon. And we can do the same thing for the proton NMR. So we look at the chemical shifts and we can identify the type of proton. And in an earlier video, I talk about different proton and carbon environments. So the number of signals gives us the number of chemically equivalent carbons or carbon environments. Same thing for the proton NMR. The number of groups of signals gives us the number of chemically equivalent hydrogens. So all these different techniques, these 4 techniques, are giving us different information about a structure, and we have to piece this together. So let's get on to the splitting then, which is what this video is actually about. A good way to figure out the structure of an unknown compound from proton NMR data is to draw up a table that looks something like this. So we've got 6 columns. We've got the label, we can call it A, B, C, and in any order we can label on our graph the groups of signals or the groups of peaks A, B and C. I've just done it left to right. Then from the data sheet that I showed you earlier, we can write down the type of hydrogen responsible for each of those peaks, A, B and C. We can write down the chemical shift value that goes with that as well. And there's something called integration. So it says here under additional information, the integration pattern is 2 to 3 to 3 at these chemical shift values. Now this tells us how many hydrogens are contributing towards that signal. So at this value, which is here, there's 2 hydrogens contributing towards that. So perhaps that is a CH2. At the signal at 2.1 parts per million, there's 3 hydrogens contributing towards that. So perhaps that's a CH3, and so on. Then we write down the splitting, so we could say this first 1A is split into 4, or we could call it a quartet. So quartet is just the fancy name for this splitting pattern when a signal splits into 4. And then B, that's 1 line, so that's called a singlet. And C is split into 3, which is called a triplet. Now, applying that concept called the n+1 rule, the number of peaks that a signal is split into is equal to the number of hydrogens on an adjacent carbon atom plus 1. So if that signal is split into 4, that means there's 3 hydrogens on the next door carbon. If a peak split into 1, that means that the next door carbon has 0 hydrogens attached. Now, if a carbon has no hydrogens attached to it, and we suspect it's an ester, from this information in the infrared, and from these types of carbon, from the carbon NMR, we also suspect it from the molecular formula, and there's some more evidence of an ester here in the types of hydrogen as well, then this is probably to do with this carbon here in the ester. So this is the ester functional group, where the R groups are a carbon chain. So you can see this carbon has no hydrogens attached. It's got 4 bonds, so it can't have anything else attached to it. So that's what's probably happening here. And then if we look at this last signal C, the peak area is 3, and the number of adjacent hydrogens on the next door carbon is 2. So if we've got a peak worth 3, then that's probably due to a CH3. And if it's next to 2 hydrogens, it's probably a CH3 next to a CH2. Pause the video here, have a look at all this data, and see if you can come up with a structure that fits all this evidence.